This lesson is let T be in R2, map to R2 such that T of x is equal to AX. Find the basis B for R2 with the property that T subscript B is diagonal. So here I have a matrix A, and make sure you remember how to do A minus lambda I. Again, remember how to do A minus lambda times I. That's from the other previous lessons. Okay, after that, do the determinant of A minus lambda I. So A times D, and then -6. -6 gives me +6, but there's another negative, so become -6. Multiply this out and then combine like terms, put them in highest order power to the least. So I got lambda squared minus 5 lambda, and then factor it out. So I just have lambda minus 5. So my eigenvalue is lambda 0, because this one right here has nothing, so 0, and this is -5, so +5. So again, where did the 0 come from? Because there's no parentheses, so 0, and inside parentheses, opposite of it, so +5. After that, instead of putting lambda, you put the 5 in, so A minus 5I. This is the solution after you do A minus 5I. After that, do row operations and then label all of my terms according to the x, and it comes out to be -2, 1, and then this will be our vector 1. Again, remember how to do row operations and how to put all of the terms in the x. Okay, so next we have our second lambda, which is 0. So put 0 in. Well, 0 times I is just 0. So it comes back to the original matrix. So A minus 0 is just back to the original matrix. Do row operations, and then after that, make sure you put all the terms into the correct x. Okay, put all the terms into the correct x. If there's a fractions, get rid of that fractions. So these are our two vectors that we have, and these two vectors are basis or eigenvectors that belong to eigenvalue 5 and 0. One more time, this is our basis or eigenvectors that belong to 5, 0. Okay, after that, make sure you put it in P equal V1, V2. This matrix is the P, and it contains all of the basis or eigenvector that belong to the eigenvalue. This matrix is only the eigenvalue, and you put them in diagonal, the rest just 0. Okay, so again, this matrix is the diagonal matrix, which contain all of the eigenvalues. Okay, so just put it in the diagonal, and these right here is our 0. So, and if you remember again, this version here, and this last one, all three of these are in the same, they have the same solutions, just written in different format. Okay, so this is to check A, this is to check AP equal PD, and this is to check the diagonal matrix. Okay, your eigenvalue matrix. So all three of these versions are the same, just rewritten in different format. Okay, now we're going to check if this is true for the example that we just did. So here's our D, this is our inverse P, this is our original matrix, and this is our P. So this P is here, this is our basis or eigenvector to the eigenvalue, this is the original matrix. This matrix is the inverse of this matrix. One more time, this matrix is the inverse of this matrix. Okay, and for the sake of time, I hope you remember how to find the inverse of a 2 by 2, so we can go a little bit faster here. And you just multiply it out. So this row times this column is this -5. This row times this column gives me 15. This row times this column gives me 0. This row times this column gives me this 0. Bring this matrix down. Repeat the process again. This row times this column gives me 25. This row times this column gives me 0. This 0 times this column is 0. This column times this column is also 0. Now multiply 1/5 all the way through, so it gives me 5, 0, 0, 0, which is our diagonal matrix, where I have all of the eigenvalue, which I have from the previous right here. So here's our diagonal matrix with I have all the eigenvalue, and this right here is our basis or eigenvector based on eigenvalue 5 and 0. Again, this right here, this form, this and this, they're all the same. It's just rewritten in different ways so that I can find certain things, but it is the same format, just written different ways. And this is how to check to get my diagonal or eigenvalue matrix. Okay, this is my diagonal eigenvalue matrix.